I started, then I go to YouTube. Wait. Go live, yes. Yes. I clicked. Yeah, it's blue. I clicked it. Yeah. Yeah.
Hello, I am
Yes.
Corrado Falcolini from Roma Tre University, and I'm very happy to be part of this project of a Kurdish mathematics school. Today I will talk
Yes.
about regular polygons and the approximation of pi. Regular convex polygons I will call Pn with n equal sides
okay?
and all equal angles suggest many different geometrical
and
questions.
I can connect to YouTube and see
from the approximation of pi to possible straight edge and compass construction, and also some application to phases of polyhedra, regular or semi-regular. The connection with the arithmetic properties of the number n of its side has been the key to a complete description and understanding of some of these questions. On the other hand, assuming pi known with high precision, we will show that the sequence I will call small pi n equal to n times the sine of pi over n represent the ratio of the perimeter of the polygon Pn with the diameter of the circumscribed circle. Whether capital Pi n, which is the sequence n times the tangent of the angle pi over n, is the ratio of the perimeter P of P or n with the diameter of the inscribed circle, apothem of the polygon. This implicitly gives a numerical approximation of pi itself. So with pi is between n sine of pi over n and tangent of pi over n.
Perhaps for 1 hour it's okay. Then probably the program itself will reduce it.
Trying to discuss some of these problems with the use of computer programs allow graphical visualization, symbolic and numerical calculation, which are now part of the tools in mathematical education at different levels. I want to recall famous mathematician George Polya, who wrote beautiful books on learning mathematics, and in particular mathematical discovery, where he discusses explicitly of visualization in problem solving. Here I present some of these questions at different level of complexity, suggesting answers with image and animation. So we start with some history. The relation between measure on regular polygons and the approximation of pi goes back to Archimedes and this famous value of 20 2 divided by 7, which is 3 plus 1/7, and this is more or less 3.142857, which is close to the value of pi by just 1 times 10 to the minus 3. So the first 3 digits were already correct. In fact, this number was obtained by computing the perimeter of Polygon with 96 sides, and this is because the number 96 is simple because it's 6 times 16, so this means that Archimedes did his work working first on the hexagon, which is a very simple figure, and then he divided by 2 the size of the polygon 4 times. He did also the same thing with this was with circumscribed polygon, and he did the same with inscribed polygon inside the circle, and obtaining the estimates from below with the number 3 plus 10 divided by 71 with this approximation of pi. So you can see that already you obtained a very good approximation up to the second digit of precision. If we look a little bit closer, and we know that the value of pi is 3.1415, so 0.8 is 7 times 10 to the minus 4 close, whether 3.1428 is 1 times 10 to the minus 3 close. So the approximation with the inscribed polygons is much closer to the approximation of the circumscribed polygon. But this is a general fact. If we use the formulas for the length of the side of the inscribed or circumscribed polygon with n sides, that I will discuss in a moment, we can see that the 2 approximations are related to the sine or the tangent. So the difference in these 2 approximations, in fact, can be evaluated by taking alpha equal to pi over n. This means that this formula for pi n is sine of alpha divided by alpha, and if we subtract the value of pi, we get the ratio between the 2 errors in this approximation from below and from above, that goes to 2 when alpha goes to 0. So when n goes to infinity. So this means that the approximation on the left is always twice better than the approximation on the right. If we want some curiosity about what one can do with computers and with numbers very easily, the curiosity is this: the number 1 divided by 7 as a period in decimal digit representation which is 6 digits long. In fact, this is the longest possible period for number 7, because the maximum is the denominator, the number in the denominator, -1. So 7 minus 1 is 6. But the other fractions is 10 divided by 71, which has a much longer period, which is 35, which is exactly half of the maximum possible period for such a denominator. If we look at the formula that I recalled about the difference in precision with these two approximations from below and from above, we can see if we take if we use these factors, so we can divide by 3 the difference between the two approximations, and the approximation that we get, instead of taking the mean of the two numbers, so we take 1/3 of the difference, we get a precision that arrives up to the 4 digits in the approximation itself. Now let's go to some specific question that I will try to answer during this talk. So let Pn again be a regular convex polygon with n sides, equal sides. The first question is, what is the minimum value of n, so that Pn is not distinguishable from a circle? Second question is, what is the minimum number n, so that the ratio between the perimeter of Pn and the diameter of the circumscribed circle is at least 3.14. And this is precisely pi n that I wrote before. So when is pi n larger than 3.14? Then I will discuss briefly the problem for which n is the number cosine of 2 pi over n, representable using square roots. Finally, for which n is pi n constructible using only straight edge and compass. Let's start with the first question. In fact, this problem is not well posed mathematically, because first is not objective, is subjective in some sense, but also because it depends on the side of the picture. So so what does it mean not distinguishable? So let's try to write down a circle and a polygon with 3 sides, and then let's go to increase n. So we go to 4, 5, 6, and as soon as n becomes a little bit larger, we can understand better the question. If we increase n, the polygon becomes, of course, closer and closer to the circle. But of course, this depends on the sides of the circle. We already, with a very small circle, we would say that the two figures are already undistinguishable. But if we fix the sides, for instance, if we take the maximum circle that we can draw on on a computer, or also the maximum side that we can draw on a usual sheet of paper, A4 shaped piece of paper. We can fix the scale, and we can go on and see when they looks undistinguishable. In fact, I cannot ask you to tell me stop, but I can go a little bit further, right? This, I think, is already a threshold, probably one possible answer. There is not a unique answer. This is why also the problem is not well posed. But probably we were helped by also the thickness of the sides and of the circle, and also by the color. So let's try to do the same experiment without the circle. Now I will go a little bit faster, and we can see the angles, and as long as we don't see angles anymore, or the figure seems not to move anymore, we can say stop. So probably you might stop around 50 or go also up to 60. All right, so as you see, between 50 and 60, for sure, the polygon looks very much like a circle. So we answered the first question. Let's pass to the second one, which in fact is a well-posed problem. What is the minimum number n, so that pi n, remember that pi n is the perimeter of the regular polygon, so with n sides, with respect to the diameter of the circumscribed circle. So in this, so when this number for which n, this number overcome 3.14. Somehow this is a question which can be related to how good is from the visualization point of view. How good is 3.14 as an approximation to pi? Then we will relate these results also to the first question on visualization. So let me give now proof of the sequence that I wrote for the approximation of pi. You can see here for n equal to 3, we have the regular triangle, and r is the radius of the circumscribed circle, and we can relate L3 to r by simply taking the diameter and see that this angle is, since it insists on the chord L3, like the central angle, the blue angle is exactly half of the central angle, which is 2 pi over 3, because n is equal to 3. So this is pi over 3, and thus, and since the triangle is inscribed in half of the circle, it is rectangular triangle, and so the side L3 is the the diameter times the sine of pi over 3. So this is general and it works for any n. And moreover, the apothem of the triangle, which is this height from the circle perpendicular to the side, L3, we can relate it also L3 to A by saying that, of course, we have two radius here, and so we have an isosceles triangle, and the angle, the blue angle, is again half of 2 pi over 3, so it's pi over 3, and here we can use trigonometry applied to the triangle, and say that the one side, which is L3 divided by 2, is equal to the other side times the tangent of this blue angle. And so for any n, Ln is twice the apothem times the tangent. So this is the approximation of pi given by the two sequences that I present before. So we can see that this construction gives the answer for any n. So now it's very simple to say what is the minimum number n, so that pi n is bigger or equal than 3.14. We simply calculate implicitly, of course. We assume that pi, as I said before, is known with high precision. So implicitly we can take the pi over n, the approximation pi over n, for increasing value of n. We can and see when it becomes larger than 3.14. Let me tell you that is very well known that this problem has a solution with the hexagon, because if we want to overcome the value of 3, so the first digit of precision of pi, if we want to arrive to the second digit, so 3.1, since this sequence is increasing and is lower than pi, we will have one precise answer. If we want to see when pi n overcome 3.1, so an approximation with 2 digits of precision of pi, is for n equal to 12, the minimum n for such an approximation. So we can try to guess probably another digit. We might arrive to 6, 12, I don't know, 24, for instance. So let's go and see. Now 24, we are still close to 3.132, which is a little bit far from 3.14. So we have to go on, and we arrive to the precise answer. The answer is 57. The answer to the question is 57. It's the first n for which the diameter of the perimeter of the polygons, of the regular polygons, the Pn divided by the diameter of the circumscribed circle, overcome 3.14. So let me say that this answer is close to the previous answer. If we go, you see, if we go to 57, the circle looks, the polygon looks like a circle, is almost undistinguishable, and this number is precise, the number that gives the approximation using measure on polygons of pi itself up to 3.14. So let me say as a final comment on these two questions that in fact the approximation 3.14, that is the one that is always used very soon at school level in education, is not so bad. In fact, for visualization problem, it can be regarded as very good. What if we continue after 3.3, 3.1, 3.14, if we continue with 4 decimal digits or 5 or more, if we call k the approximation, the digits of approximation of pi, and if we call the truncation of pi up to the kth digits, as you can see here, then we can solve the problem with this table. So we look at that with 3.14, the answer was 57, previously was 12 and 6 for smaller precision, but for higher precision, we see that we can get with n very large, and we can also study, if we like, the rate of convergence of such a sequence on K. Let me stress that such a table required simple construction, which is this one with a while command, and the most difficult part, since we have the sequence, is to take the truncation of pi, that required some commands using, as I will do for the rest of the talk, the program Mathematica, but I could have used another program on symbolic manipulation other than numerical one. So it's a simple formula that students, for instance, can write down and try to go on and answer questions for a higher K. Let's go to the next two questions, which relate the regular polygon Pn with the cosine of 2 pi over n, so the cosine of the central angle of the polygon inscribed in a circle, when the number cosine of 2 pi over n is representable using square roots. And the final question is for which n is pi n constructible using straight edge and compass. We will see that these two questions are very much related. So using Mathematica or GeoGebra or any other symbolic calculator is or the table in the usual textbook in high school, we can see that for some simple angles, we know the answer, and the answer is very simple. For instance, we know that the cosine of 2/3 of pi is minus 1/2, the cosine of pi is minus 1, and the cosine of 2 pi is 1. We know that the cosine of pi over 2 is 0. We probably have to do some calculation, small calculation, to go to the Pentagon and write down the formula for 2 pi over 5. In fact, this number can be expressed with square roots, in fact, precisely using the square roots of 5 in a very simple way that I will not discuss precisely. We know that the cosine of pi over 3 is 1/2, and the cosine of pi over 4 we can in fact construct or calculate with trigonometric identities all these numbers, but for n equals to 7 this cosine can be written in terms of sine, but not in terms of square root. Is that an accident? Do we need more precision, or what? This is what we want to discuss. So let's use again the program to ask to produce, given the number n, not k, sorry. So k is equal to n in this case. So to go on over the 8, so go to 9, 10, etc. Using simple commands to radicals. In fact, we can see here that we are using only this, in producing this table, only this command. So the program in an automatic way is trying to put the number cosine of 2 pi over n for given n or k in radicals. And we see that for n equals 7, it gives a very strange answer, which in fact contains a power of -1. So with the square with the root 7, the 7th root of -1, so using the square root of unity, which means that in this automatic way the program is not able to give an answer with simple radicals. But going on for n equal 10 is okay, and 12 of course, and more. And also for higher number, for instance 17, the roots becomes not simple. There is the radicals over radicals, and so it gets more complicated. So somehow the answer is not good. Sometimes the answer is good, but can be a little bit complicated. So having this in mind, we can produce a table writing down only the radicals when they appear in a simple way, and let's relate the number n in red when this representation with square roots is possible, and also let's make factorization of the number when it becomes when the representation is positive, when we have a positive answer. In fact, we can go on saying something of particular cases. So for instance, we can see that when n is a power of 2, the representation is very simple, and in fact we can look for simple formulas for any n power of 2. as you can see. In general, we can probably, if we go back, we can see that the positive answer is for special prime numbers, for instance, 5, 3, 17, and for combination of these numbers, for instance, 2 times 5 or 3 times 5, with powers of 2. So we see, if we go also further, so 34, the problem has a solution because 34 is twice 17, and 17 had already a solution. If we take 60 or 64, it has a solution, but if we take, for instance, 57, the number that answer the second questions, this is not constructible using, well, this is not, this is not, the cosine of 2 pi divided by 57 is not, there's no representation using square roots, all right? And we can go on. Now the answer to this problem was given by a famous theorem of Gauss in 1801, stated that for a constructible regular polygon, n should be the product of any power of 2 and distinct prime Fermat's numbers, so which are numbers of the form 2 to the power 2 to the power k plus 1, when as long as these numbers are prime. So apart from products, polygons are constructible for prime Fermat's numbers 3, 5, 17, 257, 65,537, and in fact this is it for prime Fermat's number, because these are the only prime Fermat's number known up to now. And these are all constructible, and in fact the relation between the fourth question, the constructability with straight edge and compass of the polygon Pn, is strictly related to the expression of cosine of 2 pi over n. So the same conditions works also for the table that we have seen for the representation in terms of square root of the cosine of 2 pi over n. If we want to write down a list of all constructible polygons up to this Fermat number, this is the complete list. We see the 257 and all the other factorization with distinct prime Fermat numbers and powers of 2. Let's now again take only the numbers that are the polygons within that are constructible, and so that there's this representation. If we go over, we can see that the representation in terms of square roots can become more and more complicated, as you see. Let's go over. The length can become, as you see, larger, and but we arrive to 257, and we see the Mathematica writes again the cosine for this case, in this strange way, that was a negative answer. So it looks like that the programs consider 257 not constructible. So is this an error or what? Well, the problems can be solved. So the problems of why we have this answer for a number that should be constructible for Gauss theorem, since 257 is a Fermat Primes number. So let's try to get the answer in this case using some modular algebra, as suggested in a very nice article of Christian Gottlieb in 1999. The article title was "The Simple and Straightforward Construction of the Regular Polygon with 257 sides." Using his constructions, we can write down a code which is not so long for n equal to 5. So the use of modular is written here. We get for some numbers, we get the modulus 5 of some powers, of all possible powers of base 3 raised to some integer power. And when we look to the modulus of such powers with respect to number n equal 5, if we look for all possible linear combination of such powers in this multiplicative group Z n with n equal to 5, with some calculation where which were not all done in the article of Gottlieb. So, we can reproduce the construction of radical for cosine of 2 pi over 5, and also we might construct the polygon using such calculation. So a very few line programs gives an answer in terms of a list of numbers of products, let's say, and a second list with respect to the linear combination of such powers in this multiplicative group. So with these two lists, which are very simple for n equal to 5, we get the answer. You can see this is this vector that we evaluate here, and if we evaluate it, sorry, we have to run this again. Run the lista pro and the lista rev again. As you see, in a fraction of a second we get the correct answer, and if we try to write down the cosine directly, the program gives directly the radical version of this cosine. Right? So we checked the calculation for n equal to 5. If you go to n equal to 17, the interesting thing is that we can get lista, and we can get the two lists. Okay, they are not so long. As you see, they are done all automatically by the same lines of program. We just change the number 5 with the number 17. We get the result. Again, we are using only this function vector that is evaluated here. With this new evaluation, we get the answer in a second, and if we get the answer that we saw in the previous table, we go to we get this answer. We got the answer already. If we evaluate the cosine up to the, so these two formulas looks not quite similar. They use the same square root of 17 because n is equal to 17, so this is not the case, an accident. But if we want to approximate the value of cosine of 2 pi over 17 up to 300 digits, we get this answer. And if we take this number, which is twice the cosine, in fact, so if we divide by 2, we get the same precision. Okay, so we have found a way to produce the representation in terms of square roots for the polygon with 5 and 17 sides. But why not to use it also for 257, like Gottlieb suggested in his article? And if we do the same as before, we have to change, well, this is the same in fact, we have to change the lists, and you see that the lists are a little bit longer. With these two lists, we can get the result with few seconds of CPU time. In fact, I need, well, a few seconds, as I said, and this is the final solution with these numbers, which are again roots of some numbers. To get this, to make again the calculation, I have memorized this. To go quicker, and if we now print all these numbers, for instance A14 is here, so these simple symbols means all these radicals, and the same thing for the others number. So if we use this, we get the final answer. In fact, if we get the cosine up to the 500 digits, we get this number. If we use the same calculation using square roots, which we called these variables, as you see, that we have just evaluated in a few seconds, we get it divided by 2, and we use all the substitution that I showed you, we get exactly the same answer. So we have a representation in terms of square roots given by this procedure, and we have evaluated it in few seconds, and the point is that the representation is very, very long, as I showed you. One of these number is this one. Okay, so if you substitute all this number of all of them are the same length inside here, we get the final answer. So it is possible, we knew it from the theorem of Gauss, but also it is doable, it is writable with few lines of programs and few seconds of CPU time nowadays. The interesting thing is that we can go and do the same thing for the next Fermat prime number, and the only point is that the two lists that we need in order to produce the final answer are much longer. So I can show you the first numbers. These are divided by lines because of the construction, and if I go, you can see that they are related to the number 2 to the power. The number of entries is related to 2 to the power n. So n is very large, and this number are very large. So I'm not needed. This is the second list of numbers that we used before, and with the same length. But you can see that so there are a lot of zeros, but also many ones. Okay, so in principle it can be done also for the last prime Fermat numbers known. Let me say something about regular polygon construction. Let me say only something about some graphical functions that I will use. So let me produce constructible numbers. How do I do this? Well, as I briefly discussed before, the constructability is related precisely to the representation of cosine of 2 pi divided by n by radicals, and that in the proof of Gauss, on the proof that the constructive proof that I gave following Gottlieb, is related to solution of intersection of lines and circle. So to the solution of iterative solution of equation of degree 2 at most. All right. So so if we start from 2 points that we get as the origin and the unit, so the 2 green points are at unit length segment apart, we can construct by taking circle using these first two numbers, we can construct other 4 points. So in one step we have 6 points. We start from the first 2. In 2 steps we can do the same, but we get many more points, as you can see. So we get many intersections and many more points. In fact, you can see that all these brown points are the possible points that are constructible in 2 steps, just because they are intersection of circle and straight edge that are done using previously constructed points. And this is precisely the definition of construction with straight edge and compass, which was already present in the first 3 axioms in the Euclid's elements. Using precisely the construction that I showed you before, we can see that we get the construction of the pentagon starting from the first 2 points. We construct the line, then we construct the 2 possible circles starting from these 2 points. So with 2 steps we can construct. Let's go a little bit faster. We can construct the intersection with 2 step construction. Then with the 3rd step we can construct the point P3, and then the point P41 and P42 that gives by a straight line the point P5. So with 6 steps we get finally the radius of a circle that gives us P7. So in 7 steps of the construction that I discussed, we get the construction of the pentagon using precisely the construction of, let's say, Gottlieb construction. We run out of time, so let me just show you that if we get all possible points in 4 steps, we get this nice picture, and it's very difficult to produce more point steps because of the high number of points in the picture. So here we don't get yet the cosine of 2 pi over 5 because we need 7 steps. To finish, let me show you some construction related to polyhedron. So let's go on space, in 3D space. So we started, studying a particular semi-regular polyhedron. You can see regular pentagons and faces with regular triangles, 80 of them, and 12 pentagons in this semi-regular polyhedron. In fact, they are called Archimedean. So it has 150 edges. If you make the calculation by the other formulas, you can get it, or if you try to count directly, you get this answer. And this particular polyhedron, I want to discuss only, just to finish, the truncation. So if you get a polyhedron, then you can truncate by taking the middle point of these sides, and you can cut the pyramids with the previous vertices, and you can do the same twice and produce some nice picture. So let me, this some nice picture. It's related to this. Starting from here, you can get to this with more faces. The faces are not regular anymore. But with these faces, you can give the same color to similar faces, and this gives nice patterns on this new polyhedron, not regular anymore. If you do one, twice, and you cut again, you truncate again 6 times, you get a nice shape, a nice polyhedron. If we go in this site form www.formulas.it, which contains the courses, the mathematics course in the Department of Architecture in our university, and we go to animation, we get a YouTube animation that I want to show you just for final minute. Here it is. And this animation was done by Gianmarco Todesco and myself, who thought about this idea, this realization, and the music is by Roberto Dautilia. And you can see the first part of the animation. We used we showed this animation in the year 2011. That was the 150th anniversary of Italy as a Unitarian nation, and so you can see the construction of the enumeration of the number of such polyhedron that sum up to 150, and if you have the final minute, if you go on, we use the truncation to produce I have to finish, so the truncation to produce nice color, and if we go on with the truncation, we can get even better drawing, and this is the final part, and you can see different coloring of the faces of such an interesting non-regular polyhedron. All right, so we are arrived to the end of my presentation. I want to go back to my presentation to show you the bibliography for a moment, and also thank you all. Bye.